Hello everyone, welcome to my channel. I am Zach Peterson and I am here today to answer your questions from my videos on the Altium Academy channel. Of course, whenever you have questions about PCB design content you see on the Altium Academy channel, if you leave a question there, I'll probably include it in one of these Q&A videos. Let's go ahead and dive in right now. Now, this first question comes from one of the podcast episodes on the Altium Academy channel, and this podcast episode is with Reinhard Neurieder, CEO of Dentaflux. The comment says, interesting topic. One important thing missing here is the I/O connector protection for overvoltage events like surge, burst, and ESD. Zach mentions I/O protection, but that is not fully covered. Probably easy to implement with an AI rule. So just a brief bit of background here. Dentaflux is an AI-based online platform for EMC analysis, and what the tool does is it uses AI and it generates recommendations for how a PCB layout should change in order to pass EMC testing. Now here, the commenter is bringing up something about I/O protection, such as with TVS diodes, and I think that's an important point. The design that's being looked at here in the demo is from one of our design review submissions, but as I recall, it did not include TVS diodes on any of the I/Os. Now, because this is operating on your PCB design data, the data, particularly the components, are parameterized and they do contain component descriptions, so the AI does know what types of components are in the design. I think in this case, because TVS diodes were not included specifically on those I/Os, of course the system didn't check for things like I/O placement, what ground it's connected to, those types of issues. So of course it didn't give any recommendations around TVS diodes either. I think it would also be a little repetitive if this AI system just constantly mentioned adding TVS diodes to every I/O. I think it's much more important for you as the engineer to understand when you need to use TVS diodes and implement them appropriately and not rely on AI tools to do your job for you. Pow! Let's go to the next question. This next question comes from our PCB design challenges for 5 through 6 gigahertz radar design video. And if you remember, that video is answering a question that I got on LinkedIn asking whether or not it's feasible to design a radar system that can operate in the 5 to 6 gigahertz range. The question asks, I'm here to understand how those cheap human detection circuits you can find on AliExpress work. I'm curious, has anyone managed to make a DSP with an ARM MCU instead of an FPGA? Is it possible? Well, this is really two separate questions, and I'm not going to answer the ARM MCU question or the DSP question. I'm going to defer to Phil Salmony because he has a lot more experience doing that on embedded platforms, and I think he would be the guy to answer that question. Now, about the cheap human detection circuits that you find on AliExpress, I can tell you with certainty that those are probably not 5 to 6 gigahertz radar, and they're probably not any other kind of radar. They're probably just ultrasonic. Now, an ultrasonic detector essentially just uses a high-frequency pulse of sound that you cannot hear. It looks for a detection, and then using the speed of sound, it can calculate distance and then determine if somebody is within proximity. Of course, when you're too far away from the sensor, the reflected beam will be too weak to be registered by the sensor, and so then it thinks that there's nobody standing there. So those cheap human detection proximity circuits, most likely they are just ultrasonic sensors. Now you could build your own ultrasonic sensor using, for example, those little Arduino hat modules and an Arduino. And maybe we'll do a project like that here in the future. This next question also comes from the 5 to 6 gigahertz radar design video. The question asks, could anyone send me this PCB download link, the one that Zach uses in this video? Please. There are actually two different examples that are being used in that video. One of those examples is our power amplifier module project, which is done in a different video on Altium Academy, and I've published the project files on my company website. Go check out the link in the description and you can download those files. You'll also see a link to the original video where we go over the power amplifier module design. Now, the other design in that video, with the one where we show all the patch antennas, That design is actually a Texas Instruments reference design. It's the AWR2243 Boost reference design. Now that reference design is very useful if you're going to be designing anything that operates in the 77 gigahertz band of radar, specifically automotive radar. So that design is really good because it illustrates a few PCB design principles that you'll want to follow if you are going to build a system operating in that range. Also, of course, go subscribe to Altium Academy because I'll show you how to do it there, and subscribe to this channel and I'll show you how to do it in a later video. This next question is on a totally different topic. It is all about sizing pads in a BGA footprint, and this question comes from our Understanding BGA Pads video. Now, this question looks specifically at the reduction in pad size for collapsing balls on a BGA package. Question asks, sir, as per the table, collapsing BGAs, we do a reduction as per the solder ball diameter. This means the PCB pads should be less than the solder ball diameter, but in a non-collapsing BGA, we increase the PCB pad size as per the solder ball diameter. My question is, in a collapsing BGA, 0.15 millimeters, I'm not sure what dimension that's referring to, with 15% reduction, and in non-collapsing BGA, we want a 15% increase. Is it correct? Okay, listen. This is like third grade math. If you're an engineer and you're designing PCBs, you should be able to do this yourself. And I'm going to point you where you can find the limits on pad size reduction or increase for non-collapsing and collapsing balls on a BGA package. If you look here on screen, it's right here in this blog that I have published on the Altium website. You can see here in this blog titled, What's in Your BGA Land Pattern and Footprint? You can see that there are two tables in this blog. One for collapsing balls, and it shows you the variation in the size of the landing pad underneath the BGA for collapsing balls. And then you have the same table, but for non-collapsing balls. So you can see it very clearly right here. If you want to use a 15% reduction or increase, I really don't care. You just want to make sure that it's compliant with the IPC standards. So go to this blog, take a look at that table. This table will tell you if your calculated pad size is correct. This next question is a related topic because it is about BGAs and specifically the number of layers needed to fan out a large BGA. The question says, Zach, maybe you should remind, for the young channel followers, the rule of thumb for BGA fan out to number of layers. And my reply is, you could also remind them. Now, I know I'm getting a little snarky at these comments, and that's okay, right? But there is a rule of thumb regarding the number of layers that you will need in order to fan out a BGA. You can figure out the number of signal layers that you will need based on the number of rows of balls in the BGA package. Now, if you're at a large pitch BGA, such as 0.8 millimeters or 1 millimeter pitch, you can use rows of 2 balls each. And for each row of balls going into the center, you will then have 1 signal layer per row of 2 balls. And if you are at a fine pitch BGA where you're probably going to need micro via in pad in order to get into the inner layers, you're then going to have 1 ball per row and you're going to use 1 signal layer per row. So I've gone over this in a few different videos about BGA fanouts and setting up design rules for BGAs. Check out the link in the description to see what I'm talking about. There is a video in that link where we actually show how to fan out an STM32 BGA, and we go over the guidance in the datasheet and check to see whether or not the number of layers that they recommend in the datasheet is actually accurate. So I think it's a good learning experience. Go take a look if you want to learn about BGA fanouts. Switching gears, this next question is all about length tuning and noise on differential pairs, and this comes from our classic length tuning and differential pairs video. Let's take a look at the comment. This comment comes from Wilfred's Winkles, and he says, no, there is no mismatch. The induced noise cannot come later because it's from the same source. The noise is on the edge of the lower signal, but should subtract in a similar way. So this question deals with the induction of noise onto a differential pair. And noise can come from a variety of sources. It doesn't have to actually originate at the differential driver. Most common form of noise that induces itself onto a differential pair is from crosstalk. You could also receive EMI from some other source, although if you have a ground plane close to your differential pairs, the EMI susceptibility tends to be quite low. But really, most important is going to be crosstalk from some other signal that's near to your differential pair. Now, what happens with noise on a differential pair when it encounters a length tuning structure? Well, when we have noise on a differential pair, we would like for that noise to stay as common mode noise because the differential receiver will suppress common mode noise. The problem is if that common mode noise travels through a length tuning structure, it can become differential mode noise. And so this is called mode conversion. It's the conversion between, of course, common mode and differential mode noise. So this is one of the reasons that we might like to reduce the size of length tuning structures where possible. And of course, where you place that length tuning structure also matters. Best practice is to put it close to the area where the length mismatch arises. Now it is 2025, and every year at the end of the year, I do a wrap-up of the Altium On Track podcast, and I show some of our best moments. And the 2024 On Track podcast looked at 4 big themes. And of course, one of those themes was AI. I mean, you'd have to be living under a rock to not know about AI at this point. Now, we have a question here from a viewer regarding the AI trend. When can we expect something similar to Copilot in Altium so that many routine tasks can be solved by a prompt rather than hours of manual drawing and setting up? And my response here is, it's in the works. So I don't have any inside information about a specific product being developed by Altium. I know I put a lot of stuff on the Altium Academy channel, but they do not give me any of that advanced information about new products. What I can tell you is that I have been working with some external people to try and develop the knowledge base that would be needed for such a Copilot. And there are a lot of LLM tools out there that help expedite that type of work. You don't have to make a custom model in order to do that. Now, will this ever end up in Altium as a standard feature? I can't tell you. Probably the easiest path forward for a third-party developer is to create an extension. You could then give users access to the extension either for free or through a license, and then they could access that inside of Altium Designer. Now, I'm not a software developer. I don't know everything that goes into developing an extension for Altium, and of course, I'm sure it requires a good amount of consultation with the Altium dev team. But I can tell you that I've participated in some work on this. Other people are working on it too. We'll see what happens in the future. Now we have a follow-up comment on this thread here on this video. CState30 writes, as a software person currently transitioning into EE/ECE, Copilot seems nice at first, and then you end up just doing it over manually. It's always almost good enough in my experience anyways. Well, that's the thing about AI and PCB design. With PCBs, there are just so many possibilities to lay things out, and most of them are incorrect. And I think it's really hard to articulate in a very clear language what is going to be the objectively best solution for every single layout. And so of course it's going to be very difficult for a tool like a Copilot to be able to do it correctly on the first run. I think this also illustrates that even if you do get a Copilot type of tool for Altium Designer or for any other PCB design application, it's never going to remove the role of the designer or eliminate the need for a designer to drive the tool. This is really the same thing that we've seen throughout the entire history of technology. Whenever there's a new kind of automation that comes around, those who embrace it and understand how to implement it into their workflow are the ones that win. So, will a Copilot eliminate the need for a PCB designer? Absolutely not. I think it's just going to change what we do. Let's go to the next question. This next question comes from one of the 1-minute design reviews, and this again deals with TVS diodes on an RF line. TVS diodes are important for protecting from strong RF levels into the LNA. It will be damaged without. I would disagree. That's not really the point of a TVS diode. TVS diodes are supposed to protect from, for example, ESD or surges and divert them back to ground rather than allowing them to propagate into a component, whether it's an LNA or some other component. So Understanding what TVS diodes do is very important because, of course, that will help you select the right diode for your particular interface. And in this case, the right TVS diode is going to be one that has very low capacitance. And I actually run over some of the other technical specs that you need to know in another video on the Altium Academy channel, and it should be coming out soon. So make sure to go over to the Altium Academy channel, hit the subscribe button, and you'll get to see more of my responses to these questions on this 1-minute design review. And finally, we have a question about the new wire bonding feature in Altium Designer. So I mentioned the wire bonding feature in a previous Q&A video on my channel. Let's take a look at this question. The question asks, what facilities are available for wire bonding? Great question. Where can you get wire bonding services? Well, if you work in semiconductor testing or prototyping, you'll probably need to do wire bonding at some point, and you don't have to go overseas. Now, there are a lot of overseas facilities that will handle this for you, but if you're living in the US or Europe, there are also local facilities that will probably do it for you at lower volume. And generally with wire bonding, it is typically done at lower volume. I live in the US in Portland, and we have an Intel facility nearby, and I didn't even know that there was a company near that Intel facility that did wire bonding, but there is a company called Cascade Systems Technology, and I just found them through Google. So I guess the moral of the story here is if you need some wire bonding services, just get on Google and you might be surprised to find a facility near you that can handle wire bonding assembly. Thanks for watching this video, everybody, and thanks for leaving those awesome comments and questions on the Altium Academy videos. If you want to see more PCB design content, go over to Altium Academy and hit the subscribe button. You'll be able to see videos from me as well as other awesome PCB design content creators. If you like these Q&A videos, make sure to subscribe to my channel, and I'll see you next time, folks.